Hello, can anybody hear me? Yes. Okay. Thank you. Thank you. All right. Very good. So, welcome to week number 7, lecture B. All right. So, today is the last week, last lecture for our signal in the system. We spent some time, very good time on Wednesday talking about convolution and so on and so forth. So I hope you enjoyed the topic. So today we are going to focus on one thing that's called realization. Okay, realization. So today I'm also going to do a kind of innovation about doing a whiteboard only lectures. Okay, so let me see if I can do better this way. To hide floating control. So the reading materials is on our here. It's regarding realization part. So it is signal and systems. It's realization part. It's called frequency response system realization part. Okay. So this is a realization part. Okay, the real system realization part. You guys see my screen? Yes. Not sticky mouse. Okay, good. So I'm trying to do highlight here, system realization. What do we mean system realization? So we are going to talk about so this is we are now on the week number 7, lecture B. So we are talking about system realization. So what do we mean system realization? So remember, I try to promote the idea of MAD, M-A-D. So when we do mechatronics synergy, we need to do modeling, analysis, and then design, okay? So for the modeling part, I hope you are going to appreciate the level of abstraction. So you have a physical world. So you have a physical world. So you have a maybe you have a electric, you have a mechanical, you have fluid, or you have thermal, and so on and so forth. You have different types of physical world systems. Okay, so this can be used, can be abstract into our different types of model. So we study the components. So we use a T type, A type, and a D type components. Okay, components. Okay, different types. So we are equipped with a linear graph method, or using our circuits like KCL, KVL type of concept, generalized to other systems. So we have learned this connection, right? For electrical circuits, we have mechanical circuits. So we have analogy between MSD. So after that, you end up with a model. So this model can be transfer function, differential equation, okay? So you have differential equation, you can make a transfer function, right? You also can have a state space, right? So a representation. So the state space is a special type of differential equation that has only order of 1, the first order system, right? So, but of a vector form, okay? So that is the model, okay? That's the model. With this model, we can do time domain analysis, and we can do frequency domain analysis. So in the frequency domain analysis, we mainly talked about the body plot, okay? Plot. We learn how to do this asymptotes, okay? Okay. So we also talk about Fourier series expansion. So we know the frequency contents. So actually, this is sometimes called spectral analysis. So if we have a sinusoid, then you have omega. If you have only one sinusoid, then this is omega 0. So you only have this vertical bar, right? So you have two harmonics, you have another bar, right? So you have two sinusoids mixed together. So in time domain, it's hard to see it very well, but in frequency domain, like this, it's much easier to see it. For the time domain, we basically talked more on like step response, okay? And the step response, we talked about several parameters like rise time, like steady state, okay? Settling time, overshoot, okay? Like rise time, overshoot, steady, settling time, okay? Okay, settling time, and so on and so forth. So that's a step response. And we just talked about impulse response, okay? That impulse response itself makes like a HFT, okay? So if you have any of the input UT, you convolute with this HFT, will give you output Y of T. So, okay. And if you do Laplace transform, they will get H of S times U of S equals Y of S, okay? So H of S is actually a transfer function, okay? Transfer function, this transfer function here. So I hope you start to see this picture, this picture. So, but why we need to talk about realization? Okay, so realization you actually already used like in a Simulink, okay, Simulink. But in a Simulink, you already can put a transfer function into a block, okay, into a block. In fact, the Simulink will decompose this transfer function into a canonic form, so that eventually they are going to solve a set of differential equations of first order, okay, first order. So our question here is, suppose you have a transfer function, okay, transfer function. Like let's do a very simple transfer function, okay? Like A3 S3, A2 S2, A1 S plus A0. And let's do something here. It's called B4 S4 plus B3 S3 plus B2 S2 plus B1 S plus B0. So the reason I want to write this one is we should usually write this thing as is 1, so that the polynomial is called monic. Okay, the highest order is here. So in this case, the relative degree is the degree of, let's call this as A of S divided B of S. Okay, B of S is monic. So relative degree here is a degree of B minus degree of A is 4 minus 3 is 1. So this is called relative degree. So in this case, it's called strictly proper. Okay, strictly proper. But if you say, wait, I also have 4, so relative degree becomes 0 in the numerator. So if this is say, oh, I want this one to be number 4, yes, you can. But then you are going to have relative degree 0, okay? Then it is called proper, not strictly proper. Then of course, if you have something called degree B less than degree A, so this is improper, okay? You know that. Okay, so I have this transfer function. It's an abstract model for a real world. In the back of this HFS, there's a real world system running behind it, okay, behind it. Sometimes I cannot do the experiment on the real world plant directly. I have to do it using a emulator. I want to simulate it, okay? Say for example, this is a nuclear power plant, okay? Nuclear power plant. So we don't want to directly experiment on that. So we want to build something, okay, from outside. So this is HFS, okay? But you pull out this one to an emulator. So these two outputs are the same. So we call this is a realization of this original G of S. Is a realization, okay? So how to make this emulator? Of course, there are infinite many possibilities to do that. However, remember we have learned Opamps. So when we see realization, we are talking about Opamps, okay? Opamps, okay? Using Opamps plus R plus C. So you have resistors, you have capacitors, you have a bunch of op-amps, okay? And put together, so you get op-amps to mimic that. So this is actually is also called analog computing. Because right now, a lot of people know how to do digital computation. That's easy. Today, I'm going to teach you how to do an analog computing using op-amps and R and Cs, okay? So I'm going to tell you how we can make this complicated. This is a differential equation. How we can build an op-amp and RC-based system such that I can build this op-amp circuit from input to output. They look exactly the same as HFS, so we call that is a realization. Okay, realization is never unique. Okay, we from in and out point of view is correct, then it's correct. So inside you may have many and different changes. Okay. With that, I'm going to continue. If you have questions, type in the chat box. I'm monitoring the chat box right now. I'm going to move on. Okay, I'll move on. So our objective is to have op-amp and resistors, capacitors to produce an HFS. Okay, HFS. But to begin with, this is too broad. Okay, this is just too broad. So now I want you to recall your experience on the Lego. Okay, so the key point is called a building blocks. Okay, so I want to mention that this we define building blocks. Then you can, using the building blocks and connect them, you can build your any type of HFS. Okay. But I want to draw a parallel in here. So in Simulink, you actually have a library of those building blocks. Okay, a library of them, a lot. You have source, you have sink, you have a nonlinear, you have gain, you have transfer function, you have state space, you have so many. So we don't want to go this complicated libraries. This library was built only for your convenience, okay? Here today, we are going to do a building blocks of 3 blocks, 3 building blocks, okay? So what are the 3? The first one is called a gang, okay? We use a symbol of, this is a symbol using a circle, gang of K, okay? So this is a gang. This is a building block, okay? So now we are going to say the second building block is a summation, okay? So this is a block. So you put input in here, so you plus, input in here, you can use minus, input in here, you can use plus or minus, doesn't matter. So you have many of these can add together, okay? You can choose 2 as input, 3 inputs, 4, it doesn't matter. So add together, you have y. So y equals like u1, u2, u3, and the un, okay? So this is y, okay? So y equals that, okay? But you may say, hey, so I'm doing this one for you. So we ask another question later regarding sigma. Okay, so this is a sigma, y equals sigma. This is I equals 1 to n. So I have u, I, add those signals together, right? So then you may say, oh, actually I have a gain ki. Sure, you just apply building block, right? So yeah, so you building blocks. So you just use many of such gain blocks together. So for example, you can have a UI, U1, K1, then you add U2, K2, you add. So this add together. So you have UN, so you should have a KN, then you get Y. So that is this signal, right? So with a building block, you can do many such kind of combination. So let's study the next one is more important one is called integrator. Integrator. It's called 1 of S in here. So Y and U. So and Y equals basically 0 to T, U tau, D tau. So this is a YT, okay? Okay. All right. So we have 3 different building blocks in here. But I said that we need to talk about Opamps, how this is done in Opamps. So gain, do you know how to do the gain? So you have a R. Oh, it's too thick. You have R. You have R in here. Then you have usually you have negative. You have plus in here. So you put this one as a K divided by R, K times R, right? So from here to here, you have K times, but this is a negative, okay? So you need to cascade another one. So you have another R, then you have so negative, you become, so here you have R, okay? So then we say this is Y, this is U, here we have a U of Y. So I package this whole thing from here to here. So this red box in here is my K. It's my K, right? Because the K is here, right? K is here. Make sense? Okay. So the gain actually is 2 Opamps. Yeah, assuming it's positive, okay? Positive. But if you say, well, if my k is negative, if k is negative is easier, you don't need this one, right? You don't need this one. So this is to invert the sign only, right? So I assume you have many of those gain blocks. And also I should have summation blocks. So you have a Lego, right? Remember you have Lego, you have so many blocks in here. You have also so many blocks for sum, and you have so many blocks of integration, integrator. So then I just pick up from that. Then I will be able to construct my HFS, okay, HFS, okay. So at this point, I hope you start to understand our examples here. So let us check our quiz number, week 7, quiz number 2. So in this quiz, basically, I want you to try realization. Say I give you some worked out example here. All right, so you have a F is input, Y is output, okay? So I want you to show that Y of S divided by FS is 5 divided by S plus 2. So we only use all 3 types of building blocks. Okay, so you have a summation, you have an integrator, you have gain, you have another gain, right? Others are just link the wires, okay? So I only use 3 building blocks, remember, okay? All right, so let's check. So because we know that this is our, so if you have something like this, so this is a negative. If you do not do anything, that means it's positive, okay? If you say you didn't add, default is positive, okay? The negative you will need to mark. So you have something here. So remember, you have something, let's say you have something G in here. So let's say you have something here, you have H in here, okay? So in our case, H is 2. This is my H, this is my G. So let's see how we can write this one. So this is minus, this is a positive, this is a U, this is a Y. So let's check how we should write it. So in this case, U minus, this is Y times H, Y times H, U minus, this is U minus H. So this point, this signal usually is called E, okay? But it doesn't matter. So we have this E equals this one, and I times the G, I'm going to get my Y, right? So it's like a magic. So this is called negative feedback. So what I'm going to do is to write Y divided by U is what? So in here, let's do it. So let's do it. So this one will have U G minus G H Y equals Y. I move this Y term in here. So I'm going to have a U G is 1 plus G H Y. So this one will give me U is G, and you have 1 plus GH. So okay. So there's a rule you can talk. The G in this setting, the G is called forward loop. Forward, you go this way, you have G. So this one is a feedback loop. Okay, but let me use another color. But the overall loop in here is called GH. So you can see this is a forward loop. This is overall loop, okay? Overall loop, G times H. So let's apply in here. What is our case in here? So from here to the F, apply the rule we just learned is forward loop is 1 of S. Then is the G times H is 1 of S times 2 and 1 plus, okay? And then you multiply 5. That is my Y of S. This is U of this is F of S. So times this one, you will get this. So let's write. This comes out. This S comes out. You write S in here. So that Y divided by F will give me 5 divided by S by 2, right? So the manipulation of this loop is clear. We got this. Okay. But the question is, we are working in a forward way, so it's easy. Giving these blocks, I can get this one easily. But now I'm giving you this one first. Can you come out this type of thing? So that's a realization. That's a realization. So you only use the 3 building blocks to realize this thing, okay? So that's a realization. Again, this is relative degree is 1 minus 0 is 1. So this is a strictly proper, okay? Strictly proper. So let's see an example of second example here. So what's the relative degree here? It's 1 minus 1 is 0, okay? So it's only proper, not strictly, okay? That means it's possible we can write, 1 plus, okay, S plus 7, that's minus 2, right? So it's possible to write this way. Okay, it's possible to write this way. So you can see, you know how to do the 1, you know how to do the plus, you know how to do this one. You have learned this one before in the first example, right? So let's see whether we can do. We follow this one. We make this one borrowing this one. So minus 2 is here. So I have a minus 2 in here. Okay. So then I have 1 of S in here. I get this one out, minus 2. And out here, I have 7. Then I put this one here. So this is a minus, this is a plus. So this is my input is F, output is Y. But you have 1 in here, meaning Y equals F plus this thing. So you need to pull out F in here and going through 1. Then you add everything on top of here. So you have on top of here. So this is a plus, this is a minus. Do you see that? So from this one, I can see, this is a realization. So from here to here, this is a realization of S plus 5, S plus 7. But in here, they also did a realization, okay? A realization, how they did this. So let's check out how we can make this one happen. Okay, so let me do a little bit bigger. So I already worked out a realization here, okay? Because I pull out this 1 to here, okay? So you add on top, so you get this one. So it's already, I worked out following the example BA, right? So I'm now doing another realization here. Let's check whether this is correct, okay? So this is like, so yes. So you can see there's something interesting here. If I don't consider this guy, okay, do not consider this guy. So if I don't have this one, what I'm going to get? Because I know that from example 1, I have, this is S plus 7, okay, S plus 7. So if I don't have this one, it's this, okay? Now, so we need to do something different. Different. What's the difference? So what is this guy? This is y divided by 5. Look at the red realize the summation block by the y has both positive. Oh yeah, you are right. Because I use some. Yes, you are right. You are right. Yes, thanks. Okay, let me type. Thanks. Good catch. Good job. Okay, thank you. Yeah, this is great. So here, they basically did everything is positive because they didn't write positive, then it is positive, okay? It's positive. So let's check here. So if I move, this is y, then what is this? Y divided by 5, right? Okay, so we pull out this signal here. What is this signal? I said this could be E. So the E equals F is the input minus 7 divided by, 7 divided by 5 times y, right? Times y. Okay. And this one, this E, this is E, right? This is E. And this is a one, so then E plus y divided by 5 times 5 equals y, okay? Did you see that? Oh, no. I think we should do this differently. Because this is a summation. So let's say this is a y1, okay? This is a y1. So let me do this. So this is a y1, okay? This is a y1. So this is E plus y1. No, it should be y1, okay? E pull out here, and here you have y1 in times 5 is the final y, right? Final y. So this also is not true. It should be y1, 7. So 7 times y1 minus this, so you get an E, right? So let me pull out this, replace this E into here. So I have F minus 7y1, okay? Wait. So this is no good. Okay. So I need to remove this y1. I need to remove E and remove y1. I only need to care about y divided by f, all right? Okay. So what we're going to do here is we know that E times 1 of S is y1, okay? Is y1. So we know that, okay, we know that so this side is E plus y1 is 1 plus 1 of S y1 equals y, right? So E times S is a y1. Oh, no, this is S, sorry. Then E is S times y1, okay? So this should be S, okay? And E is SY1, so S plus 1 Y1, then times 5, okay? So this becomes to this equation. So I remove the E, so I need a Y remove the y. So here I have E is SY1, okay? So SY1 is plus 7Y1 is F. So this will get you to this one here, okay? This one here. So then we can write this is S plus 7 times Y1 is F, okay? S plus 5. E is, let me double check. E is F minus 7 Y1, while E times 1 of S is Y1. So E is Y1 times S. So I replace this one here. I have SY1, so times 5 is Y. Okay, sounds good. So what I'm going to have here is, so I have two new equations. One is this guy, and one is this guy. Okay. So what I care is y divided by f. Okay, y divided by f. Okay. E plus 5 y1 times 5. I think something wrong here. I think this one is wrong. It should be adding here. Should not like it's just a E 5y1 times 5, then add together. So it's not like this. So sorry, you don't have this one. So you add this 5 in here. So this one is 5y1 is S. So you don't have this one here. You should have 5 in here. Okay, 5 in here. So in this way, you are going to y divided by f. You are going to have S plus 5 F divided by y. So it's S plus 7 and S plus 5. Don't you guys see this is so tedious? Okay. And I don't know how they come out directly like this. So I know it's wrong actually. This is wrong. You should put the E pull out in here and all these are plus. Okay. So let me walk you one more time. Okay. So based on all the symbols in here, so E equals F minus 7y1. Okay. So let me do this. So this is correct. Then the second is E pull over here plus y1 times 5. Okay, y1 times 5 equals my y. So this is my y. So this is correct. Okay. Then also find out E and y1, these are connected like this. So this is E equals y1 times S. This is correct. So I'm going to insert this E is SY1 here. So this one will give E is SY1, 5Y1 is S plus 5, 5 plus S, Y1 is Y. Then the next one is E equals SY1. Then you pull out this one this side, so you plus 7Y1, you get an F. So you basically get this. So now you do Y divided by F. So you will have this one left. So we verified so far, we verified. This is a realization of this one, okay? This is a realization of this one. So it's kind of tedious. So again, let's count. Well, we have 3 types of blocks. okay, summation. And here another summation where we use two summation, okay? Again, another gang, and one integrator, okay? Did you get it? I hope you get this. You're able to understand this worked out example. There is slight problems in here regarding, so there's no such thing there. So that's example B, okay, example B. So even for this type, I derive, giving this block diagram, how to write this one. We already spent some time on it, okay? But giving this one, then how you can get this in a systematic way and quickly you can draw it, okay? But I also give you alternative here, okay? Make use of the, this realization, okay? That's a realization. So in other words, giving op-amps, giving those op-amps, you will be able to do all this gain, sums, and integrator. I'll show you the other two later. But the point is, giving a transfer function, the system behind the transfer function might be electrical or thermal or fluid or mechanical. Then you did the modeling, then you get the transfer function. Then you want to mimic it, to simulate it. So you only have the 3 building blocks. So how you can do that? So this is one example with worked out example. So here's another example. It is called, again, this relative degree is 0 and it's proper, but not strictly proper. So in this case, we can use the similar ideas. This can be written as 1 minus s plus 7 to 7, right? Is s plus 7. So then you have this constant term. You can do the similar idea of what I did in here, right? So, but they do something differently. Okay, they do something differently here. So there's this is 1. Okay, this is 1. And then they have a integrator on the feedback loop. Okay, then you have an output. Okay, so let's apply what we learned, G divided by 1 plus GH. In our case, G is 1, and this is GH. This is H, okay, it's H. So what we do is we write 1 divided by 1 plus 1 times GH. H is 7 divided by S. This is S plus 7. So you can see there are multiple ways to do it, right? So this is the way to do it. So this is considered as a realization, okay, of this one. But remember, for example A here, so we have 5 in here, 2 in here, integrated in here. So what is the numerator? The numerator is 7, so I put a 7 in here. Okay, and it is minus 7. Okay, then I have an integrator, and I have pole is 7 here. This will give me minus 7 divided by s plus 7. Okay, then you have a 1. Okay, then you add this together. Yes, this time is plus plus. Here is to put a minus. So this is your f. This is your y. Okay. But the question is, we have run through this one. You have more than one ways to do the work. Okay, more than one ways to do the work. But there is, so that depends on your taste, flavor, habit, preference. So what if I want you to do something called canonic realization? Canonic realization. So this is the one I want you to finish, okay? So again, you can only use, in this case, you have a integrator, gain, summation. You have three. You know, another realization. So you can see you did the summation, integration, gain, another gain. So you can see it may not be minimum. We are not asking you to do minimum number of building blocks. Okay, that doesn't matter. Okay, we need a systematically and quickly to write this canonical realization. We'll come back to this thing. Okay, so this is a monic one. Okay, so this is B of S. Did I use a B or this is A of S? Okay, so this is A of S is a B of S. So this is a polynomial, right? So we are working on this one. So there's a 5 gain block before summation block. No, we don't have. This one is, no, we don't have any block in here. Okay. And are you talking about this one 5? No, this is something wrong. Part B. Yeah, this is wrong. Actually, they didn't draw it correctly. They should draw in here and have a summation here. So everything here is 1. Okay, is 1. The gain is 1. This one is 5. Okay. All right. Clear? I cannot wait to go through this one with you. This one. Okay. This one. So, but we are going to do something more general here. So if you, okay, sorry. So my point is, if you can do this one, then you can do the one on the quiz or anything even more general, okay? Okay. So let's continue here. Again, we have 3 building blocks types, okay? But in each type, you have unlimited number of blocks you can use, okay? Don't save blocks. We don't want you to save blocks. We want you to realize it and as quickly as you could. But what about the summation? Don't you guys feel like this is a trivial? So how to do this? Okay, simple. You only need one Opamp, okay? One Opamp in here. Okay. So if I'm talking about this one, what should I do? We just put these other, put here, you have a U1, a minus K1, okay? And minus K2. Let's do K1R, K2R, okay? So I'm talking about a K, no, probably it's, I'm confusing this one, so I was not right. So I should use a resistor here. This two is a minus K1 R. Do you guys feel strange? I'm using a negative resistor. Yeah, you have seen in the quiz already, right? So negative resistance is possible. I'm just trying to save some time. But you can say, I don't like it. I want to, I don't feel good if you use negative K1. So I do negative Kn in here. Actually, we should use K1 over Kn because it's our feedback. Okay, it's a feedback, RF. Okay, RF. Then you divide by that. So, so this is UN. Okay. So then you just add this one. So this to me is nothing but, looks like it's because of KCL, right? Okay, KCL. But what if you say you don't like this negative sign here? Easy, okay, easy. You don't like it? It's okay. We just say, I put a U1 and get you through R. Then you have another R in here. Pull out in here. Okay. So you simply if you want to put a positive sign in here, then you just use U1 is here, pull out the output, get this guy to here. Then this is your minus sign, okay? All right, so simple. Then you can do the same. But I'm just assuming you agree that this is not really needed, okay? Okay, so let's move to the integrator. So everybody knows the integrator is how to do that. So you have a Y, you have a U in here. So you can say, hey, let's check. Y is the voltage, this is 0. So the current in here is C dy dt. Okay, C dy dt. The voltage, this Y is voltage, equals, this is U divided by R, okay? It's minus, okay? Because they go here and here add together is 0. Minus. So therefore, Y equals what? Y equals minus RC 0 to T U tau d tau. Okay, so that's integrator exactly like what we wanted here. But you say, I don't like this. So that's easy. This is not 1. I can make this one by 1. How to do it? So I can do, so this number we know, usually this is linked to the time constant. So I can do in here, R, so this is R1, then I do this one here, then I can do here another R. So I allow this RF equals minus, RF equals 1 of RC. Okay, so that's okay. We can choose RF equals to that. Okay. No, actually, it's times R. Yes, it's times RC. So it's easy if I can multiply R minus RC to this one. So then I'll make this one. This is 1, right? This is 1. So this is 1 because this is 1. What I need to make this from here to here, RC. So this is equals RC, okay? Because RC times R1, okay? Times R1. So R1 is here, okay? So this ratio becomes RC and it becomes a negative RC. So what I do is instead of we put a U in here, you put, so you put like, this is U1, this is U1, this is U1, okay? So now you have U in here. So you want this one to here. How? Then you can see I put here is U, put here is U1. I pull out this wire, hook up here. So then from U to Y, from U to Y is exactly like this one, okay? It's exactly like this one, okay? So you can always scale or change sign. That doesn't matter, okay? that doesn't matter. So that's my point. So now, so if I give you low pass filters like this, you should be able to do body plot, impulse response, or whatever. That's easy. But how to do realization using op-amps? So you already can do this 3 different blocks. So you have blocks here, you have blocks here, blocks here, blocks here. But you also know that giving these blocks, it's corresponding op-amp. This is op-amp realization. This is also op-amp, okay, realization. And for integrator, you have op-amp, okay. So you can always do that. So there are 2 levels. One is using 3 blocks, okay, 3 gain, sum, and integrator. Another one is op-amp R and C, okay. So you have another 3. So 1, 2, 3. So one is op-amp, one is R, one is C, okay, and many wires, okay. Okay, so I just tell you that these and these are in op-amps. So you have many op-amps, many R's, many C's. So you can do the same, okay? So we haven't solved this problem yet. So we have issue of so we have this. Let me see if I have an idea to cut this one down. Link to save. Toolbar location. Oh, it's here. It's called this. Oh no. Okay. So let me see how I can cut this one. Maybe I should stop. No, don't do that. Let me do this. Hide this one. Go down. So I'm going to focus on this one. I'm going to focus on this transfer function to see how I can make op-amps to draw that, okay, to draw that. So what I'm going to do here is to show you, I have input is F, output is Y, okay? And here I'm having a feedback. So this is ASBS. So let me copy. So A3S3, A2S squared, A1S plus A0. You have, this is AS. This is S4 plus A3, B3, S3, B2, S2, B1, S, and B0. So again, this is relative degree 1, strictly proper, harmonic. So because this is 1, okay. How we can use 3 things, okay? That is one of S block, there's a K block, as well as sigma block, so summation block. So to systematically do this one, so we are going to focus on canonic realization. Okay, so how to do that? If I tell you, you will feel this is hard to remember. But if I walk with you, it is so nice. Okay, so I'm going to do something like this. So let me do this. So you have F. Suppose you have something like this. So I split these 2 into 2 parts. this is do you agree I can do this? Yeah, it's the same, right? So this is y. Let him assume that I have x in here, okay? Assume x in here. So what I'm going to do is x divided by f, you'll have x divided by f, you'll have x divided by f, you'll have this one, right? So this is b, this is a of s, okay? So this is a of s, 1 of a of s. This is b of s, okay? B of s. So I think you understand that. So if I write this one in whatever way, so if I cross product, I'm going to have f, okay? You have f. So f equals what? Is S4x, okay? Plus B3S3x plus B2S squared plus B4S, okay? So plus B0, okay? Okay. So in other words, if I have, also I need x, and x in here. So I need to write differently, x. So just cross product, this one to this one. So this is f. So then this multiplied by the x. So, okay. So x divided by f is the transfer function, okay? So what I do is to move S4x and get everybody else to b minus b3 s3x minus b2 s square x minus b1 sx minus b0 x. So the reason I do this one is, okay, is I want to write x, okay, write x. So this is like x, the derivative of 4, right? So if I draw, I have an x in here, okay? So I have a x s4. So if I somehow manage this guy, okay, this is a signal, remember, this is a signal. If I make this signal to integrate it, what I'm going to get, okay? So if I integrate again, I'm going to do s squared x. If I do an integration one more time, I'm going to have sx. If I do integration one more time, I'm going to have x. So these are the signals, okay? These are the signals. Okay, these are signals. So I can see, these are the signals, okay? Signals. So this signal equals f. So equals f, okay? Equals f. But you have a big sigma in here. Okay, so this is f coming in, which is positive, but it will minus 3x, so I just minus 3b in here. Then add this one, okay? So I'm going to add this one minus, so I'm going to add this one, okay? So I use all the minus here, I convention, okay? Then I'm going to do another one here. So it's a b1 minus. So this is positive. Because I always use positive, I don't want to mess up things. So then I have another one is minus b0. Did you guys see that I only used 3 types of blocks? These are gain. These are the integrator, okay? Integrator, gain, and sigma. But I only end up in here. This is my x in here. So let's check. because X in here, pull out in here. So Y equals A3. So clearly this one equals A3 S3X, okay? And A2 S2X plus A1 SX plus A0X. So I have X in here. So the X is A0. I go through the A0, okay? Then I have SX is go to, I use a different color. So this one will get you my A0. Then this one will get you A1, okay? Then you add everything together, you get Y, okay? So here you have S square here, so you have A2 in here. So then you have S3 in here, you got A3. Okay, so we're done. Basically, later you can insert all those blocks with Opamp realization. However, if I draw this huge, box in here, this box is nothing but this box. Okay, so it's called a realization of that transfer function. Don't you guys see there are some rules you can observe? A polynomial you happening here, okay, and B polynomial you happening here, okay, and you have highest term in here s to the power 4. So that 4 actually is the number of integrators in here. You have 1, 2, 3, 4. And this is outputting here. So this is outputting here. So S4X becomes like that. So this is a canonical realization. You can write down this one in no time. Okay, so let's check this one now, how we can do this. So easy. So how many integrators I have? So I put this one here, I put this one here, okay? So what I'm going to get here is sigma, okay? So this is my F, this is my Y. Okay, so what I do is this is a plus, this should be also plus here. So this will give me -6, right? This one will give me -5, positive, okay? So you need to flip that this sign here, okay? Be careful. And what you have is 28. This is my X, so that means you have 28 in here. Then you add this one, sigma, so it's add 28 SX here. So this is X, this is SX. So then you get this one be 4. Okay. So this is using a 3 building block, given any transfer function, you can immediately get this one out. Okay, you need to practice this one. Okay, you need to practice this one. And so we have done this one. But if I say do a realization, okay, do a realization, okay. So I want you to draw the canonical realization. So then this is done. This is correct. Okay. But if I say, please, I need canonical realization at the Opamp level. Opamp level. So what are you going to do? You need to make all these components in Opamp form. Okay, then you insert it in. So just be careful. If you are positive, you need a cascaded. So this is the positive. Okay. So you need to be careful about the signs. In this case, you need to go back to this one. Like I explained to you, gain blocks how you use Opamp, and you have an integrator and summation. So all these things can, be realized in the Opamp level. Okay, Opamp level. So I hope you didn't get messed up by the realizations I did here. Okay, but let's check whether we can do this one using our canonical way to do. But to me, you have one integrator. Okay, so then this is x, this is sx. So this sx will be equal to, you have f in here, you have sigma in here. So then I'm going to have, give me a second. So I'm going to have a -2 in here and -2 in here. So this is a plus, this is a plus. So then I also should have a 5 in here, okay? And I get a y. So this is a minus sign here, so this is a minus. So this is exactly like canonic, is exactly like this. Following our canonical way, you can write it immediately. Okay, so I told you then you can do this one immediately. So this pathway now is a piece of cake to all of you. From here to here. Now it's easy. You have learned it, right? So the question is, I followed along with integrate Opamp and gain Opamp. Is there Opamp involved with sum? Good question. Let's review this. So this is a summation here, okay? Summation here. So you have many signals that you add together. So it's just like a sigma in here, right? And even you have different gains, okay? So you just like this one, right? Like this one. So the thing is similar to the KCLs, okay? So you have a node in here, you have node in here, so you have, whatever signal just put together, or just KCL, you add them together, right? But remember, you have to use Opamp, okay? If you without Opamp, you add things together, you short circuit your spark, you have a your catch fire. Don't do that. Okay, so then I also mentioned about this is negative versus how to remove this negative sign, how you can make this coefficient to 1. So I think this argument is quite simple. Okay. Questions? Our timing is perfect. We have done everything we have. So congratulations. At this point, you can say that, I'm equipped with signal systems. Yeah, I'm an engineer, not a technician. Okay. All right. I'm not insulting technicians, but I hope you'll make this MAD from the beginning here, the MAD. This big picture, MAD, modeling, so level of abstraction. So live at the engineer's level. And I think the Simulink MATLAB simulation is always good for everybody to practice to help you to understand better. And so in fact, today we also learned how to do analog computing, okay? We did analog computing. So analog computer originally was built in exactly the same way, okay? Opamps, So the first computer is called ENIAC. So you can Google it, ENIAC. It was built to solve differential equations, okay? Like this one. So this is differential equation. Differential equation, okay? Now you know what's going on within that analog computer, okay, the ENIAC, okay. Unfortunately, you cannot visit my office. I have an analog computer in my office, so I can show to you. It's very, very interesting. Well, I think today is good timing. We have learned about realization. So we're going to see next week, we're going to start our new journey on controls. So I'm a real hardcore control guy. So I hope you'll enjoy the next few weeks of controls. All right, see you later and take care, everyone. Stay healthy and stay positive. Okay. Not COVID positive. Stay COVID negative, but life is positive. Okay. Bye bye. Take care.